Okay, it's equal to mg.
G.
What's also equal to? What if we have two masses in space?
Big G times M1 times M2.
No, M2 is not there.
Big G times
no
big
M2.
M.
Yeah, there
What?
Wait, but
M1
if you say force of gravity is
Wait, hold on.
G is
Oh,
equal to
wait.
that. not
Hang on, force of
I
gravity.
have some more
Well,
convenient
because the mass of the
notation.
force of gravity.
Wait, what about gravitational
Oh.
field? Isn't that like another
No.
wiggity whack thing? Gravitational
Yeah.
field.
Okay. Yeah. Well, we'll get to that later.
Oh, yeah,
actually,
sure.
all right. So, what is gravitational field right now?
Gravitational
G?
field on
Look,
our planet.
Look,
is
okay, I can
like
tell you what the gravitational
9.81
field is.
something.
Right? If you're given this equation, let's call this the mass of an object. And let's call this the mass of Earth. Right?
Wait, just put like big M and then little m.
Okay, sure. The mass of Earth will be big M.
No, should
Wait,
be
is the mass of Earth like a known constant? Like
Yeah.
we need to memorize?
No, you don't need to memorize it. They'll tell you if they need it.
And, same
And
for,
then,
like,
okay, so
radiuses.
when we do mg, we're always talking about the mass of the
50 kilograms.
object, right?
Yeah.
So then if we just cancel out the mass of the object, you get small g is equal to g mass of Earth divided by r squared. So that's how you calculate gravitational field strength.
Wait, I said I thought it was acceleration.
Yeah, gravitational acceleration, same thing.
And that could be applied to any planet, right? If you replace
Yeah.
the mass of the Earth.
Yep.
Yeah. This can be that's how you calculate gravitational field strength of any planet. But do you guys remember the equation for gravitational potential energy?
MYG.
What?
Negative.
Big G
Big G.
Oh.
M
Yeah.
and 2 over just R.
I think
Yeah.
I was thinking of the one.
That's the equation for big G. There's a way to prove it using calculus, but if you kind of just want to memorize it, then you can. Also, if you want to think about it as force times distance, this is like not really real physics, but like force is this thing times distance is r, so then you just take away the r. You can kind of think about it like that, but I wouldn't do it because that's not really what it is in reality. But anyways, this is the equation you just gotta memorize. What does it mean to escape a planet?
It's to no longer be in the control of the field, like the field of gravity of the.
Okay, well, actually,
To go out of orbit. Essentially.
So, like, the force. Or wait, no, that's not the correct way to put that.
what do you, alright, what
Like,
it means?
Your velocity is great enough to overcome. No, not velocity. I don't know. Like, you're going this way quick enough to like overcome the force.
Tangent. It's something.
Well, it's just you need to have enough energy. So go. Alright, so remember, like if you're trapped by the gravity of something, your energy is gonna be like negative some number, okay?
Mm-hmm.
But if you're not trapped by any gravity, then your energy is gonna be zero. Your potential energy due to the object, and this is what we're looking for. If it's escaped the gravitational pull, then the potential energy is gonna be zero. Right, that's the instance where it becomes distance infinitely far away from the object.
Yeah.
Okay.
And so if we're trying to find the escape velocity, then let's remember the equations. Delta U is equal plus delta kinetic energy is equal to 0, right? Because this is a conservative force, so this equation must always hold. Okay. And we also know that delta U is equal to the U final minus U initial, okay? What is U final? What's the final? Yeah, final 0,
Oh, okay.
right? This is what we call it as the final, the end result. If we're trying to reach escape, we're trying to escape the entire gravitational field, then at the very end, the distance will be at infinity.
Okay.
And then the equation.
Oh, like it'll eventually reach infinity.
Do you know why distance is infinity?
Wait, write out the equation again.
Alright, so U is equal to negative G m1 m2 over r.
Okay.
As r approaches infinity, this number approaches 0, right?
Yeah.
Yeah.
So that means it's eventually gonna reach infinity.
Yes, it will eventually reach infinity. And
Why
that's the
is-
energy that we were worried about.
Why did you
Right.
put U is equal to negative C?
I just call this some constant. This is if it's trapped by a gravitational field, it's going to be a negative some number, okay? But once it's not trapped by a gravitational field, it's going to be 0.
Okay.
Alright, so I'll just erase this because it might be a bit confusing. Alright, so now what's the initial potential energy of the spaceship?
What?
What's the initial potential? What is UI? We found U final is equal to 0. What's the initial potential energy?
It's some number.
Minus negative. I'm just going to copy this equation again. Right? G times mass of the spaceship times mass of whatever.
Earth.
Yeah, Earth, we call it Earth, divided by R, some R that it's originally at. Okay? Okay, I'll call it from the surface to escape completely from the surface of the planet. So like in this instance, you just look at the radius of the planet. So like the radius of Earth is gonna be some number, and that's what you're worried about for this R, right? I'm just plugging it into here. Okay, so the change in U is equal to positive G oh whoa, that's so weird. ME over RE. And that kind of makes sense, right? It's going to be a positive change in potential energy when it's going further away. When it's gaining, it's gaining the most, this is the most potential energy it's ever going to have by being infinitely far away from the object. Okay, so now let's plug this into here. G E over RE is equal to plus.
Wait, I get why the final velocity would be 0, right? Escape velocity would be, the final velocity is 0. I get that, right? So why is delta U plus change in kinetic energy equal to 0?
This is just the equation for conservative forces.
Oh,
For
this
gravity
is-
is a conservative force, just remember this equation. That equation
okay.
always holds for conservative forces, yeah.
Okay.
Alright, we know that,
You can set them equal to each other, right?
yeah, you can
Yeah,
something equal to, so like this is the energy it needs to gain in order to reach escape velocity. So what is it? So like this is like kind of the energy final. Remember energy final is equal to energy initial. So like what's the energy final is going to be all gravitational potential energy.
Yeah.
But then the energy initial, right, is going to be all kinetic energy because we're trying to see what's the initial kinetic energy it needs in order to reach escape velocity. So 1/2 m of the, okay, m v squared, and then you cancel out the m's.
And then V is your escape
Yeah.
velocity, right?
So yeah, v is your escape velocity, so 2me over re. Oh wait, re
Yeah, that's what I did.
square root, and that's your escape velocity.
Wait, and isn't there a G as well?
Oh yeah,
Yeah, that's what I got.
yeah.
Wait, wouldn't it be is equal to negative 1/2 mv squared because delta U is equal to g m times me plus.
It has to be equal to 0.
Yes.
What is delta U? Delta U, obviously when it's at infinity, it's 0, and then minus negative g me over re, so that's positive gm. That makes sense because it needs to gain potential, gravitational potential energy in order to reach that far
What's
distance.
the closing parentheses?
Oh. Okay, and
No.
then, so this is going to be g me over re is equal to negative change in kinetic energy. What is this change in kinetic energy? Kinetic energy at, that means kinetic energy
Hold up.
final minus kinetic energy initial, right? What's up?
So 0 minus g
Is positive g.
so kinetic energy is g of m times mass of Earth over r. Is that what's happening
No,
here?
this is equal to negative change in kinetic energy.
Wait, what? How'd you get to step 0 minus negative g of?
This is just change in potential energy. U final minus U initial, right?
Okay.
U final is going to be at 0, and U initial is just going to be this negative number.
Okay.
Remember, that's just the equation for potential energy.
Okay.
Okay, and then we have this, right? Is equal to negative change in kinetic energy.
And the chain of kinetic energy is k of e final. Oh, and that's you get that.
Yeah.
Okay.
So what is kinetic energy final? Kinetic energy final has to be 0. That's the minimum escape velocity, right?
Yes.
Which means that it just has enough energy to reach d equals infinity.
Yes.
Which means that kinetic energy final has to be 0 when d is equal to infinity, right? So then this is just equal to the kinetic energy initial, right? So we know that g me over re is equal to kinetic energy initial.
So by the time it reaches d equals infinity, it's not moving.
Nope, it's not moving.
Okay.
That's the minimum escape velocity for the object. Right?
Okay.
Okay, and then we solve it like this. So yeah, this makes a lot more sense.
Yeah.
Taking another picture, just.
Let me erase this. Actually, I should not have erased
Yeah,
it.
that was a solid.
Control Z.
It's alright. What was it again?
It's 2G
Oh,
divided by R.